Okay, this is the second podcast about spectroscopy, and in this one we're going to talk about spectrophotometry, which is a type of spectroscopy. Okay, so spectrophotometry is a quantitative measurement of transmitted or absorbed light, and we're generally talking about visible light. Sometimes we have some near UV or near IR, but we're really talking about this range right here. A little bit of UV, a little bit of the IR, but we're mainly talking about visible light. Okay, so if you think about, let's say I have a solution, and I put it into this little thing that looks like a test tube that's actually known as a cuvette, which is like a rectangular plastic tube. And I have light that is shining, and I shine it through the solution. What happens is some of that light hits particles and gets deflected or gets absorbed. Not all of the light goes through. Okay, so the basic idea of spectrophotometry is I can determine what percentage of the light comes through the sample. And as you can imagine, if I have the same light source and I had a more concentrated solution, less light would come through. Okay? And the solution would, to my detector, my eye, it would look darker. Okay, so we're going to talk about Bayer's law. Bayer's law relates the concentration of this colored solution to the amount of visible light that goes through, or the amount of visible light that gets absorbed. All right, and here's the equation. A is equal to ABC. Pretty easy to remember, right? Sometimes you'll see this written as A equals epsilon BC. Sometimes this B will be written as an L. Okay, those things stand for. So A is the absorbance. How much of this light gets absorbed on its way through? The A or epsilon, depending on which source you look at, is called the molar absorptivity constant. It's a constant that is unique to each substance. Okay, so if I have a blue solution or a green solution, they'll have a different molar absorptivity constant. And it's actually also unique to the specific wavelength. So at a certain wavelength, there'll be some molar absorptivity. Okay? And C is the concentration. Okay? So the concentration is nothing more than the molarity, moles per liter. Okay? Now, what I forgot to include here is B, which is sometimes included as L, and that is path length. And it is generally in units of centimeters. The nice thing about these cuvettes that we're going to use in the lab is they are 1 centimeter by 1 centimeter. So the path length, B, is generally 1. Okay, now if we take different samples with different concentrations, what will be the same is their molar absorptivity. The path length will be the same. And then we have this direct relationship between absorptivity and concentration. So we're going to go through and talk about how we can use Bayer's law to determine concentration. And this is what we're going to be doing in the lab. So we start off with some solution, right? We have some solution we're trying to figure out how much of a colored species is in it. Okay, so I make up some solution that has that colored species in it, and I measure absorbance. What I do is I put it into this box, and this is called a Spectrophotometry, this little box we're going to use in the lab. This is a little cuvette. I put my sample in the cuvette. Spectrophotometry has a light source. It goes through. It has a detector, right? And it is able to measure what comes out. And what you get when you do that is you get this absorption spectrum. And what you can see is the different wavelengths of visible light down here, and this is the absorbance. Okay, so here I have a sample that's absorbing a lot in the yellow region. Okay, I select an optimum absorbance wavelength for this material. Now, in general, you want something that's got high absorbance. Okay, so you want to pick a wavelength that has high absorbance, because you're eventually going to take this solution that you have made up and you're going to dilute it. And you want to make sure that when you dilute it, it's got enough color left that you can actually see some interaction with the light. Okay. Now, two things you don't want to do is you don't want to have something that is more than 1.0 in absorbance, because the absorbance might be too high. The machine might not be reliable enough to give you good information because it's absorbing too much. Okay, and you also want to be greater than 0.2. You know, 0.2 is somewhere down here, and that again is so that at 0.2 most of the light's going through. There's not enough particles in there that you get good data. So I'm going to pick a point. You know, this is 550 here, this is 560. I'm going to pick a point of 565 nanometers. Okay? Okay, so I'm going to I've made a solution of known concentration of the species that I'm interested in. It might be, in our lab, it's going to be a copper plus 2 ion, so I make a solution that has copper plus 2 in it. And I take that initial sample and I go through a series of dilutions. So I take this concentrated solution, I take 1 milliliter of that, put it in a test tube, and I fill it up to the 10 milliliter mark. So it's got 1 milliliter of the concentrated solution and 9 milliliters of the stock of water added to it. I do the same thing with this solution. I take 1 milliliter of it and I add it to a test tube and I dilute that with 9 parts water to the 1 part solution. And I keep doing that, and as I do that, my concentration is going to go down. I'm basically moving the decimal point over my molarity as I go. Okay? So I'm making this series of dilutions of known concentration. Okay, so I'm going to take this wavelength that I identified up here, the maximum absorbance, I think we said we were going to be at 565 nanometers. I set that on my SpectraViz, and I measure the absorbance for each of these samples. Okay? I'm going to take the data that comes out of that, and I'm going to create a concentration versus absorbance calibration curve. We call it a calibration curve because we're setting up a curve that has different concentrations of the sample that we're interested in, showing different absorbances, and we're going to use that to help us figure out how much is in our sample of our unknown. Okay? According to Beer's law, you know, if path length is 1 and it's always the same for all my samples, and I have the same substance in there, epsilon should be the same, I should have a straight line. Okay? And that straight line should have go through the 0, 0. It should not have a significant y-intercept. Okay. So once I've created that calibration, then I take my unknown sample. And this is the sample that I'm trying to figure out what its concentration is, and I measure its absorbance in the SpectraViz the same way, same wavelength that I did for the other samples. And I use that to determine the molarity of my known concentration. So let's say I have this calibration curve, I put in my sample, and it gives me a absorbance right here. I just read the graph and I come over to the concentration and I can read off the graph what my concentration is. Okay, so that's what we're going to be doing.